for that, we call it is also the velocity. But this is actually the real classical mechanical velocity. But this is some kind of the acceleration. Okay, this is the equation up to here. We have this equation. So let me just to expand that. So we just expand this equation. So rendezvous on the Q I make Q I dot plus we have it two summation actually. Okay. Okay, look at that. What's the BQI? So this is a Q dot I. According to the Hamilton equation, that's given at the partial derivative of the Hamiltonian with respect to the momentum, and this is just P dot I, and this is minus Hamiltonian with respect to the QI. The problem is here, this is on the Q dot I, on the QI. I always consider that zero. The reason is that I'm thinking that when you pass to the Hamiltonian, so QI and Q dot I are considered as independent parameters. Independent parameters in the Hamilton picture. So you can safely set this zero, but you can use another technique also. For example, are you not sure? Okay, just replace the Q dot I. What is this? Pair. And if H be a very well posed function, not always, if this is a continuous function, derivative function, and derivative have an infinite number of derivatives, so you can shift the place, you can shift the derivative and write it that like this, And what is the partial derivative of H with respect to the QI? Is minus PI. QI with respect to the, no. This is a partial derivative of Q dot with respect to QI. So Q dot is partial derivative H with respect to P. So the partial derivative of P, partial derivative of this respect to Q, yes. What is the partial derivative of H with respect to the Q?
Minus PI.
Minus PI dot. And this is, you know what is the PI dot? VPI, Yes? And they cancel. So they cancel. So they cancel. This is a, but I'm referring, I like to consider the QI and Q dot I as an independent parameter in this multivariable function over the phase space. So I safely always set this zero. So you get this equation, partial derivative of this plus sigma I over 1 to n QI this is a zero. It's very convenient to define the something called a Poisson bracket of the two functions f and the g with respect to the q and pair. Poisson bracket of f and g with respect to the coordinate q and pair is partial derivative of f with respect to q and g with respect to the pair minus f with respect to the pair, g with respect to the q. If you have more than one coordinate, just replace the I here, so you can get that. This is very common. So using this convention, you can see that this is just nothing, just Poisson bracket of the rho and h. I want to ask you this week you will do something about the Poisson brackets because it's very important, and this is one of the missing parts in your former course like classical mechanics. I'm not sure that you studied that in the detail, but we need it. So some preparative about the Poisson brackets. So I will ask you to do that in the homework. So I will ask you, and the Poisson bracket was the first step to build the quantum mechanics. Before the quantum mechanics, we know all the information, almost all about the phase space. Also a statistical mechanics existed before the quantum mechanics in some sense, thanks to the calculation of the Planck about the black body. So we had something earlier. Einstein also. Einstein did the calculation about the photon and the boson mainly. So, but the starting point for any quantum theory is that to use the Poisson bracket and finding a quantization rule for the Poisson bracket and make it. And almost not all the theory have that. For example, electromagnetism, you can do that. So you have a photon, or you have a quantum theory for electromagnetism. You have a quantum theory for some other fields, but you don't have the quantum theory for gravity, for example. You never can consider gravity as a very easy form of the quantization, like just replace the Poisson bracket to that, except some new works. So they try to back to the main idea and consider the gravity like electromagnetics in the similar frame and they do the quantization. This is very advanced. That's not the place which I needed to talk about that. So you will find that in some public lecture I will deliver maybe here. So this equation is given for us, give to us everything. So the statistical systems are categorized according to this equation. We have a stationary case when this is a 0. Stationary case is that if you have the phase space for the one system, and if this is the portrait of the row for some time, at time ti, for example, the stationary portrait is that this tumor, it looks like the tumor. The form of this tumor repeated for any other finite time in the same form, and it doesn't change the form and doesn't change that. So the same portrait will be repeated here, almost the same, just if the pattern is stationary. It's like the fluid. If there is a fluid in the channel and nothing changes in this fluid, like the density, like the velocity, so the shape of the fluid will remain the same through the whole motion. So think that they should be the same form. So I'm not very good in painting, but just think that they should be the same. So this is the equilibrium condition. This is the equilibrium condition in the statistical physics. Equilibrium. Any system out of this regime is considered as a non-equilibrium system. And the statistical physics for non-equilibrium system is very hard to talk. We are talking about the system which, in the phase space portrait, the density have the same pattern after the several times. But you think that maybe you think at the minute